Let's get this show on the road. I believe our integrity session is working. We're through with welding. Now we're going to get into different forming processes. Shearing, a process for straight line cutting on flat stock. It is performed by forcing an upper and lower blade past each other with the desired offset. Usually one blade is stationary. We have a foot shear in the lab that some of you have used. We have that 12-inch one where it has that big long arm on it that you can press down and cut things. But anyhow, shearing makes a straight line cut. In fact, scissors work the same way. You'll notice though that they have a little bit of an angle, because if you tried to cut all at one time, it would take much more force than if you look at even our shear. It comes in at an angle, so it's only cutting a little bit at each time, then it works its way down. Or with that foot shear, you need 5 or 10 people to jump on it to get it to cut if you try to cut it all at once. And then, you know, these schematics that they have. You try to get the blades a certain distance, and there's a formula for that, and we'll show you in a little bit. If it's too close, you create a fracture on a fracture, and it makes for a mess. If it's too far apart, it kind of stretches the material a little, and then finally tears, fractures, and rips, and makes a bird edge, you know, those sharp little metal edges. And so there's a fine line and to getting it just right, depending on the material that you're using, how soft the material is, or how hard it is. So I think this clarifies what shearing does. Yes, you can just cut things off. Depending how you put it in at an angle or whatever, it's going to cut those pieces off. And then it shows you tolerances, surface finishes, and we'll get into that later on with our profilometer and all that stuff. But anyhow, it shows you in micro inches how close it is. Tolerances plus or minus, not a tenth but 1/100th of an inch, depending on what you're cutting. Smaller, thinner materials, more precise operation, you can get to what, 5/1000ths of an inch. But basically what we're showing you here, I guess, is for sheet metal and thicker plate metal. Anything over 1/8 of an inch is considered plate. Anything under 1/8 of an inch is typically sheet metal. There's a foot shear kind of like ours, only this one's probably better because it's not made in China. But anyhow, it cuts, you know, it has all this guard, so when you slide it in, when this comes down, you're not going to cut off your fingers. And all this is, what happened was they had all of this, and people would still get their fingers in there. So then they have to put a clear plexiglass thing in there. And the reason you still need that is so you can look and see if you're cutting right on the line to make sure you're going to get a nice, neat cut. But it's just, it's amazing. Here's one that's electric. And you hit the pedal, foot pedal here, and cuts it. Now that'd be nice. And so it's probably hydraulic. Yeah, hydraulic shear. The hydraulic pressure gives you obviously more strength. And again, if you look at our blades for our shear, they have a certain shear angle. It's just kind of like a guillotine. They used to, if you've ever seen anybody, I don't know when they first, we went into Iraq to clear out all the quote-unquote terrorists or whatever. And they were beheading people that were working for the oil companies and stuff. And they try to cut their head off, and even though their sword was sharp, you know, you've got your, I know this is kind of gross, but I'm letting you understand how this all works. But you know, you got a bone in there, your spine and all that, connecting your head. And they just cut it straight when they came down with that sword. Well, the deal is you got to come at kind of an angle. And so then they have to start hacking it to try to cut off the head. Just, you know, everything they do is sloppy. Bad job. So you got the shear angle, and then what they have is the rake angle too. where you have the rake angle of this blade too. So the thinner it gets, it's only making contact right there, cutting it, and then it moves along. And so you only need enough force to cut that one section right there. And then it just keeps moving the force down the line. Like I said, it saves a lot. And it gives you a nice cut. And there was an art to the people back in the day, in the French Revolution, all that, when they took a guillotine to everybody. And they had that thing at a certain angle and the rake angle just right. And it would cut those heads off perfectly. Nice, smooth cut. And they had the right pressure and all. That's why they were real tall, because they had to get enough weight, you know, from that thing dropping down to cut it just right. And they said if they did it right, before all the blood drained out of your head, that people could still talk and think for up to a minute afterwards of having their head cut off. It's kind of spooky to me. You know, you cut somebody's head off and, you know, they can still talk and look at you, so it's kind of gruesome. But anyhow, I digress. I'll keep moving here. Anyhow, what I'm saying is all this is built upon, you know, our the industry and getting all of this up to speed when we got into the industrial age and all that. They learned from what they had done in the past. So, the tolerance, the surface finish, how good a smooth cut you get depends between the shear blades, the clearance between those two shear blades, the rake angle, if you got that right, the material thickness, the material width, you know, how wide this thing is you're cutting, the hardness of the material, and actually how far, if it's held down well enough. Sometimes if, you know, that one bar thing that came that had the plexiglass thing over it, that helps hold it down. If it doesn't hold it down well enough, it slips, then it's going to move a little and then create a burr and other things. So there's more to it than you think. And then, you know, squaring shear, you can cut angles if you have the thing set up at an angle. Bigger ones, you can cut bar stock. And here's a bow tie shear. So it just depends. That way you got your angles coming from two sides and cut down on it. So it just depends on what you're doing. And go from there. Alright, shearing summary is used for straight line cuts on flat stock. Takes place between the upper and lower shear blades, produces burred and slightly deformed edges. Now, if you get just a hair burr, where if you run your finger across it, you're not going to cut yourself, then that's fine. That's good. That's the trick. But you don't want to where it's really jagged, where then you have to do a second operation, have to file it, sand it, whatever you got to do, and that costs money and time. Blades can be mounted at an angle to reduce the force required so that the relative length of the material being cut at any given instant is small. Again, so you don't have to have this huge shear for all the pressure to push down on it. So, anyhow. Then we get into notching. It's kind of a shearing operation, but you'll have two, and you can cut out squares or corners. Shearing operation by which scrap metal is removed from the outside edge of a workpiece. I said, why are they doing this? Let's say if you're making something out of sheet metal and you start out with a piece of paper, and if you just try to fold the corners and that, it's not going to work. But if you cut this section out, then you could fold up that corner and that corner and that, and then there wouldn't be this interference in the middle. So anyhow, keep it moving here. There's our actuating lever, and we have a notcher which needs work, but I'll have to fix that. And then when you cut out those corners, it falls down here. That's why they usually have something underneath it so it'll drop down. Guides, depending on your piece of sheet metal, you can adjust these. They slide up so you can get a perfect cut every time instead of having to look where the lines are and make sure you line it up. I had those in there, but people kept pushing them on ours and got it all out of whack, and so I gave up and just have you look and make sure it's right on the money. So here's before and here's after. Again, it cuts out the corners. Cuts it in here. And when I used to teach at the high school for a couple of years, they would cut it notches all the way around and make Chinese throwing stars and throw them at me when I wasn't looking. So then I had to put mirrors in each corner of the lab so I could see what was going on, and cameras. All right. Anyhow, removes metal from the edges of the workpiece, can produce different angle notches by adjusting the position of the workpiece. Directly produces re-entrant cuts not possible by shearing, which you saw. Can facilitate bending or drawing to achieve final desired geometry. Like I said, if I cut out this corner or this piece of paper, then I could fold one piece to the other. And then I could also cut like where I notch a little edge in there, but then I can make tabs that I fold over. So with that little tab folded over, it comes over the two pieces, and when they connect, there's just going to be a gap there. But no, then this tab could be folded over, and then you got something to spot weld, which we do in the lean production course, where we play with the sheet metal and all that. So if you're taking that later on in your career here at UT Tyler, then you'll see what I'm talking about here. All right, lancing, a combined shearing and bending operation where a portion of the periphery, okay, the outside edge, of a hole is cut into the workpiece and the remainder is bent to the desired shape. No material is removed from the workpiece by this process. So what they're saying is you can cut so much, you cut a slit here, and then you push it up. So you can make, or you can cut it this way where you cut it like a C and here, and then you can fold it up and you can make vents or louvers, like on a hood. You see people louver stuff. You name it. So again, it cuts it, but then as you see how this is angled, it bends it, but it doesn't cut it all the way off. Alright, so it cuts, and then because the way this thing is angled, now if it was straight, it would cut the whole thing off. It would punch it out like a punch. And this is a punch, but what I'm saying is if it was straight, it would punch out and then leave a square hole there, a round hole if this was round. But no, it's cutting it, and then just before this, let's say, would be sharp and cut it off. No, it just bends it down, and that way you've got something covering your vent. And it shows you a louver, a tab, let's say something was spot welded here, or just a regular vent. All that from your sheet metal. So anyhow, cuts a portion of the periphery of the hole, and the remainder is bent to the desired shape. Again, that's lancing, louvering, making all that stuff. Removes no metal from the workpiece. That's the big thing. It just slits it enough and then bends it so you have an opening of some type. Can use a single cut to facilitate the making of special features. Then we get into nibbling. These little handheld nibblers. I guess one works with air and one's electric. A shearing process which utilizes a series of overlapping cuts to make complex shapes. What you can do is cut curves with this, but it shoots out these little, like, small half-moon things. Well, let's see if this video still works. I tried the other ones. Let me see if this works. We'll cross our fingers here. Hopefully it's not something lewd that they changed or something. I just got to watch these.
Sir, I was going to suggest.
Boy, we got commercials and everything. Oh my
cookie layered with caramel covered in chocolate for the right side.
Cut this out.
And Left Twix makes cookie layered with caramel covered in chocolate. No, cloaked in chocolate. Totally different process. Try both.
Well, I'm getting
Twix.
All right.
We head from Expert Village. I'm Terry. Today, I'm going to show you how to use a set of metal nibblers and metalworking. Next, we're going to make an inside cut. First, I need to make a hole in my material in order for the cutting.
Yeah, he's got an air pneumatic type.
Okay, I just punched a hole with a drill press. You can use a handheld drill. I just did it because I'm lazy and it was quicker. Right now, I'm going to out down the burrs, draw a little hole here so I have something to follow. You want to lay it on the edge of the table so you can work.
And you want to hold it.
You don't have to sit there.
Makes a lot of noise. See how it's shooting out those little pieces of scrap? And it shoots them everywhere. Those little pieces falling. Instead of having to buy a big drill
If you're making a change in position, as I did, you always want to stop it, regather yourself, and then start again. You don't want to hold down the trigger and keep that mechanism.
And it's kind of safer than trying to make a big cut in metal, because then the piece, if it breaks loose, spins around and can cut you and all that. So anyhow, okay, get out of this thing. All right, back to our precious slides.
On behalf of Expert Village, I'm Terry. Today, I'm going to show you
I know this thing's going to play forever.
metal nippers and metalworking.
All right, Terry, I think we've had enough.
Metalworking tools, you do need to adhere to.
Okay, that's beautiful, Terry. We'll keep moving. All right, so anyhow, here is a bigger one that cuts it for you. It runs on air and probably has, or it has little round balls that the piece of metal, and that way you can spin it around the table, moves every which way. It's a CNC type. So just depends on what you want. And then here's one for cutting things out manually, but it's got deep enough throat where you can cut in pretty far, however deep this is, a foot, 2 feet. So anyhow. Then it shows you the action where these two rub together, but in so doing, as it's cutting, you have these little scrap slugs that shoot out everywhere. So I wouldn't do this in your carpeted living room or something like that. And since we have our lab is carpeted, I try not to use one of these. So you'll never get these little sharp pieces of metal out of your carpet. Anyhow. Before, you have to cut a hole somehow first, whether you punch it or drill it. And then once you get in there, you can cut out a bigger hole. Or here, they just on the edge, they started cutting and cut that out. So it just depends on what you want to do. So anyhow, sheet metal thickness usually does not exceed 1/4 inch. Utilizes a press with an oblong or rectangular punch and die or shear blade. Machines usually stroke 300 to 900, so that up and down like a sewing machine, 300 to 900 times per minute. And that way you can produce complex shapes, or you can cut curves instead of having to use a bandsaw or something. You can see how this is quick and easy and good to go. Because the bandsaw, you're limited on how deep the throat is before it hits the band. Whether it's a 9-inch, a 12-inch, a 15-inch bandsaw. Here, no, you can go as far as you want. So, little handheld. Then we have slitting. So let's say we have a big piece of sheet metal, and we want to make little strips out of it. Then we have slitting here. So a shearing process used to cut wide coils of material into several coils of narrower width as the material passes lengthwise through circular blades, so on and so forth. Basic setup. You have your one big coil, you move it through here, you cut it with the little knives, a little slit, and then you have, this one I guess has 2, so now we have 3 coils of material. So what they do is they have them offset, and then again you have to worry about blade clearance enough to where you're going to cut that and these things roll along and slit the material. There's a bigger setup thing. Before and after. Oh yeah, now I got it. Okay, it all makes sense, yes. Alright, anyhow, limited to relatively thin materials, 1/1000th to 1/8 of an inch. Burrs are normally present to some extent on the slit edge, so you don't want to just slide your finger across it. Same with sheet metal. People cut the sheet metal in that lean production class, and they go, "Oh, I cut my finger, I cut my finger." I said, "Well, I told you not to rub your, you cut something, it makes a nice sharp edge. It's like a razor blade." And so, and they want to feel if it's sharp, and then they got all this red liquid, and then they realize that's the blood oozing out of their body. So we have some masking tape. You just tape it up. Masking tape hasn't been touched by human hands, so it's relatively clean. So as long as you press that together, what I would do is squeeze out some blood to get all the grease and oil out of there. And then wrap some tape around it and take it off after a day, and you're good to go. This whole thing about Band-Aids, just a waste of money. I've cut my finger all the way through in places, which some of you saw last year. And I just wrapped the masking tape tight around it, wait a couple of days, it finally fuses itself together, especially if it's a nice straight cut. You let it bleed out a little to make sure you get all the contaminants out, and then you're good to go. This tetanus shot and stitches and all that. Oh man, with all the way our healthcare insurance is going through the roof now, you don't even want to see a doctor. All right, they'll want your firstborn son or what have you, whatever you got. All right, let me see what else we got here. Maybe used on ferrous and non-ferrous metals, plastics, paper, you name it. High production with control process. All right, so enough said about that. It's pretty straightforward. Then we have punching. Punching, a shearing process in which a scrap plug is separated from the workpiece. Now you're saying, well, yeah, we got that. Well, there's punching and there's blanking, so that's why I want you to know the difference. Punching is when whatever you punch out, that's the scrap. They're going to take it, they'll melt it back down or whatever they do with it, but it's the scrap, okay? So whatever you punch out of this thing, the hole, the square, whatever it may be, whatever the shape is, you're not keeping it. That's the scrap. And here, let's see if this punch press works. I don't know. Got all these things. Yeah, here's a big punch press. Excuse me. We have a handheld one, which you'll use in class. This is obviously for cutting through bigger plate. Right here, now they're actually punching the metal. Look how it does that. Can you imagine trying to do that with a handheld punch? I don't think so. Not bad. Nice and smooth. Wasn't too loud or anything. Look at all those punches. That's pretty thick, 1/4-inch plate. So can't beat that. Yeah, you can. No, you can't. All right. Let's get back to this. All right, now we're going to lose our PowerPoint because I tried to do too much with our integrity session, but then it'll come back again. Dun, 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 dun. And of course, not in the right spot, but I guess we'll take it. Okay, those are punch press. Let's see, and then here was our punch press for sheet. Let's see if this is any better. What they're punching here. No, didn't like that, did it? Let's see. Here's this guy. Oh, look, he's punching. Punching a few at a time. I don't think this is a Hollywood production by any means here, but anyhow, these YouTube things. You can make your own YouTubes. You get a lot of ratings, and who knows, make some money on the side. I don't know how foolish you can be, but look, it's punching all these holes at one time. And so that's pretty good. Is it going to work? Let's see. Yeah, now it's going. And then they got it set where it only goes so far each time. And then look at that. I guess this is done in China. I see a lot of Chinese people looking at it going, oh no. Well, anyhow, let's see what else. Yes, now they're measuring it to make sure it's plus or minus 10 inches, like most of the junk you get not. Alright, well, anyhow. Enough said there. Alright, let's go back to our... Alright, and then again, here you can punch multiple things, whatever shape you want. You know, it doesn't have to just be round. And so depending on whatever the shape of your punch and your die, the part with the hole, then that's what you get. And again, you got to worry about clearance, blade clearance between the punch and the die. Anything, it's, you know, it's a shearing process. All these are shearing processes. Before and after, you know, you can have it where it punched all this at one time if you want it. You know, a manual one, a CNC one, where it does it all for you. All right, again, punch and die alignment, punch and die clearance. So you got to have the line straight, you got to have the clearances just right. The hold down force so it doesn't slip on you. Material thickness, of course, is going to change everything. And punches will tell you the thickest material that they can punch, whether it's mild steel or some type of, you know, hardened steel or what have you. And then what type of lubricant that you may need on some of these. Punching summary is the most economical method of making holes in sheet metal or strip metal for medium to high production. As you can see how quickly it was to punch that out versus getting it to a drill press, drilling the hole, holding it, then moving it, and you know, it's the only way to do it. Can produce various shaped holes. I mean, you could get a laser cutter and a plasma cutter, but if you're doing a bunch of them, it's much easier to use a punch, and you can get more accurate and precise. And they can be made out of conventional tool steel or carbides. I'm talking too fast here. Produces a burnished area around it, so you know where it's pressing, that part's going to be compressed a little, so it's going to be shiny right around where the cut is. As you can see around here too. A shearing process in which, now here's conventional blanking. You're saying, what's the difference between punching? Well, look at this. Here, as you can see, they've used up most of the material. They're keeping the part that got punched out. So let's say they're making coins here. Let's say these are going to be dimes or something, or quarters or what have you, or whatever it may be. They're going to keep it, so that's why you see as much of the material, there's not much left to recycle here. Usually you can tell by that in itself. And here's a hydraulic swing arm blanking machine. You know, it's more kind of manually operated. And then they've got more of the production type for blanking, but it's kind of similar, you know, obviously to the punch, only here you're keeping the workpiece and the outside part is the scrap that you can recycle. So you're going to keep all of these parts. And obviously, so you can save on material cost. If you look at this, if you had a big roll and you were cutting 3 strips, well, if you angle them a little and they're closer together, there's less wasted material. Then that little quarter and a quarter and a quarter, you could get a whole nother strip out of that one piece of sheet stock that you use. And let's say you slit it into 3 or 4 sections. By the time you add up these 4/4, that gives you a whole nother bunch that you can get out of there. So you save a lot of material. Same with these that look like T's. See, we're only wasting that much versus that whole big chunk of metal. So you got to look at, see the L's here, how we position them and save material. Again, clearance between the punch and the part, and then you get that little bit of a bird edge where it kind of had to press it. The deal is to get the least amount of bird edge as possible, and then where it's smashed down there, that's going to be shinier there, and that's going to be your burnished. And they say something's burnished, it's been pressed down and kind of buffed and shined. And then here it's just showing you a die set to make this little part that you see here. So conventional blanking shears the workpiece from the parent stock as the punch enters the die. Produces burnished and sheared section on the cut edges. Produces a bird edge to some extent. Quality is controlled by the punch and die clearances. All right. Then there's a quiz on that section. Now, for the sake of time, I'm going to move on to the next section. So that'll be our first metal forming quiz. If it's not labeled quiz 5 or whatever, I think I call it metal forming quiz 1. All right, then this section will have metal forming quiz 2, and maybe 3, I'm not sure. 3 phases of shearing. Now, we talked about shearing, you know, cutting things, cutting metal. The deformation occurs on both sides of the cutting edge as the punch and die close in on the material. So it's deforming the material. Then they call penetration, where you're just starting to cut it, where you're penetrating, you're cutting in on that surface. Before, the deformation is you're just bending it in. But then when you just start to penetrate and cut that piece of metal and set up the fracture lines, they call it the penetration. Then they have the fracture, that once you cut it, it starts to tear and rip, and that's after 15 to 60% of the penetration. If it's a hard, brittle material, it takes about 15%, and then it's already cracking, fracturing, cutting along that edge. If it's a softer material, then it's obviously going to be 60%. So it just depends how ductile, you know, how flexible the material is. And then it shows you some shearing defects, depending how close or far apart you have these dies or what you've done with the material. It can be bowed. And if you look at it, we have different names for things. A twist is when, you know, the thing's actually twisted, where the two edges, they're not square anymore. Okay, so it's twisted. Bow is along the length of it, the longitudinal, I guess. The width is still the same, but it's just bent. It's bowed like that. Kind of like a bow for a bow and arrow looks. You know, it's skinny like that and bent. Camber is perpendicular to that on this surface, where this, when you cut it, this part bows out like that. Which in some cases is good. Like if you're cutting with some aviation snips or tin snips, you want it to bow, and you can see the way those things are angled. So it's out of your way so you can finish making the whole cut along the length. So it just depends on what you're looking for. Sometimes you want that, sometimes you don't. 4 zones of a sheared part. I don't make this stuff up, okay? I know you're saying this is a little much, but they do. They get into this stuff, especially engineers and all that, so it's good that you understand this terminology. The burr, like I said, is the rough edge that remains on the metal after it has been punched or sheared. Should be small enough so it does not have to be removed. A large burr is caused by the clearance of the blades being too great, and then, you know, you got that sharp edge, you could cut yourself. Then we have the zone of plastic deformation, and plastic not as plastic as in a material, man-made material, but plastic as in something's plastic and pliable. So the deformed mashed down area along the top of the cut. So where it smashes it right before it's going to cut it, because it has to put pressure on it to hold it. And then it's pressing it down and then until it finally cuts it. Area is localized because of the small amount of clearance between the shear blades. Then when it presses it down enough, squishes it, you know, you compact something, it gets shiny. So a shiny area on the edge of the cut. And then the fracture zone is where it finally penetrates that, cuts it, and that's where you have your fracture zone. And again, depending on the material thickness, how hard it is, that's what your penetration will depend upon. The capacity of a machine can be increased by increasing the rake angle. So you can angle this a little more, and maybe you can cut thicker materials, or you can cut it faster. Let's see. Too much rake angle can cause defects. So again, like here's a, let's say a foot or a hydraulic shear. You put it in there, you have this at too much of an angle, that can cause problems too. How do you know? You play with it. What you do is you look at the recommended settings, and there are machinist handbooks, different handbooks for all this stuff. And then, depending on your material, you go from there. You know, since a lot of metal's recycled, they add other stuff to it. It's never perfect. It's not exact. So somebody may have thrown a bolt in there that was hardened steel, so it may have thrown off the mix a little, where it's a little harder than it should be in certain spots. You never know. And so that's why you have to adjust it accordingly depending on the batch of material that you may have. All right, again, a twist is spiraling up of the sheared part, as we said. Something's twisted. It's easy to tell. As the rake angle increases, twist becomes more intense. Keep the rake angle as low as possible on narrow cuts, thicker metal, and softer metals like aluminum and copper. You say, well, that's about the whole gambit. Well, what they're saying is keep it as low as you can. You only increase that to make a decent cut if necessary. A bow, like we said, a tendency of the material to curl up longitudinally, like the bow of an arrow. Caused by high rake angles, stresses within the material too, like you can cut something and because the material wasn't stress relief, some of the metals, then once you cut it, it throws it out of whack, and then so it bows up. And the material thickness may not be even all the way around. Camber, like we said, the radial part where it's curving out, a radial deformation in the plane perpendicular to the bow, so you kind of like the width versus the thickness. Occurs most often on the edge, can be eliminated by taking a wide trim cut, specifying stress relief material as well for the metal. And then a defective edge, too much burr, a deformed edge, ragged edge. So, you get a rough edge of some type. That's a defective edge, normally caused by dull blades or improper blade clearances again. So, then here, if you have insufficient clearance, it produces a secondary shear because it's trying to cut it, it can't, so then it smashes it again. And that way fracture lines don't exactly meet up right, and then you need more energy because it's not cutting like it should, and then because it's rubbing too hard, it's dulling the tooling, and then the dull tool makes it even worse and worse. So. Excessive clearance produces extreme deformation because you're stretching the material more before it finally rips. High fracture angles, large burrs that can cut people, or things just don't fit right because, let's say, it goes on somewhere else, but it's got this burred edge sticking up. So it's not good for assembly. And then some of the clearances allowed. If you look in brass and soft steel, the multiplier there is 0.06 times whatever the stock thickness. Here we have 1/8 of an inch, 0.125 times 0.06. So here's our gap. 7.5 thousandths is how much gap we should. That gives you a ballpark. You try that. If that doesn't look good, you go with maybe a little more gap or a little less gap and see what happens. Run a few samples before you run thousands of these and ruin them all. And then same with other material. Depending if it's not as soft, 0.1 is fine. You don't have to have it so exact, is what I'm saying. Clearance affects the smoothness of the fracture and the pressure required. Stress, stress and strain. Here's something, and it's kind of like a human being. The internal reactive forces inside a material that are produced to resist an applied force. Okay, the force may be, whatever, how this thing's coming down and hitting it. Same with people. The force may be your spouse is nagging you about something or what have you, or your girlfriend, boyfriend, whatever the case may be. Or your mother or your father getting after you. You need to finish college. You've been in there for 12 years, for God's sake. What are you doing? All right, well, anyhow, especially if they're paying for it. But by then, usually they're not. So that's all the stress. Then the strain is when a material is deformed because a load is applied to it. So, you have all these internal stresses that people are putting on you. Oh, and I need this done by this due date. And the strain is where, like human beings, where you're actually hurt. You feel the strain, and oh God, this muscle hurts or whatever, and you have to take some Motrin or aspirin or something. Okay. So here's when a material is actually deformed because a load is applied to it, is the strain. So the stress is all the pressures, and these are the reactive forces inside the material. But then when you're overstressed, then you get strain. And that's what they're talking about here, where it actually causes some damage. All right, hardness testing. Number obtained is a measure of materials resistance to penetration. We have a Rockwell hardness tester in the back. Some of you took the materials testing course that required, and we'll be coming back. Higher the value, the more difficult to form, so it's harder. Now, when you're working with sheet metal, do you want something really hard? No. You want to be able to bend it. If it's too hard, then what happens? It rips, it tears, and that's no good. It breaks. It's just like glass. Glass is really strong, you think about it. Plexiglass is more flexible, but it scratches real easily. That's why we don't have plexiglass for our windows. And plus it crazes with the sun and all that. And glass is pretty good. You don't have any problems with it. It's just when it's, you know, I've even birds fly into glass, into your glass window, and they bounce off and kill themselves or whatever. I've had people throw rocks at glass. But when they throw big rocks and they throw them hard, that's when it finally shatters. That's the only problem. It becomes too brittle. So there's a fine line. And that's why steel was good when the steel age coming from the Bronze Age. Before you just had cast iron, you know, where you could just cast it and, you know, it's hard, heavy, and this and that. And then steel isn't as hard as cast iron. It's flexible, which you want, because when you're fighting with a sword, if it was real sharp and hard, that's nice, but if it hits another one, it's going to break and crack and break off. So you want it to be able to flex a little bit, not be super, super hard. Disadvantages, readings are sensitive to the surface conditions, the flatness, and the test procedures. And we get into that in that one area, materials testing. Yeah, a lot of times you have to put it in a machine that flattens that piece and cleans up the surface, cleans it all up, and sands it, polishes it smooth, and then you test it. So, affected by cold working near the surface, makes a soft material appear harder than it is. What they're saying about something, if the surface is just hard but below it's soft. So depending how it was cut, formed, forged, what have you, you could have it just to where if it's case hardened, just the top of the surface is hard and the whole thing isn't. And so you have to be careful about that. The way something was cold worked or bent a couple of times, smashed or whatever, and it just kind of, and so it's just the top surface is harder than the rest of the material. Tensile testing, you know, when you're pulling something apart, testing that, how strong it is, versus compression where you're pressing against it. Concrete is good for compression. It's bad for pulling apart. That's why you get those big cracks in your driveway, and that's why they put that welded wire in it. You know, you've probably seen that stuff in there. Rebar and stuff like that is to keep it held together so it's better when it comes to tensile strength. The yield point is where additional strain occurs without any increase in stress. So what happens is there's like a curve on this. You put so much stress on it, you have so much strain, or can withstand so much pressure. Then it gets to a point on that curve where you put more pressure, but that's it. It flattens out. It can't withstand any more stress, and so you've hit the yield point. Can't take any more pressure. It just flattens out. It's not any stronger, can't withstand it. So that's as much stress as it can take. And that's when you start getting into some strain, where it's deforming a little, but it hasn't ripped it or ruined its strength, but it's just flattened out. That's as far on that curve as it can take. That's the yield point, where it finally yields, and that's all it can do. Now, the ultimate tensile strength is the point at which the specimen loses its strength when stretched. All right, so here, yeah, there is no more. So here is where additional strain occurs without any increases in stress. So, yeah, I'm sorry, man. I digress here. Ultimate tensile strength, the UTS. Point at which the specimen loses its strength when stretched. So it gets to a point where, yeah, here is where the strain occurs without any increase in stress. And it pretty much flattens off, and then it doesn't have much. Ultimate tensile strength is the point at which the specimen loses its strength and stress. So then when you stretch it, then you've hit that flat part, that plateau at the yield point. Then it starts going down where you're losing the strength. So you've reached that. And what usually happens, it'll do that. It does this on the curve, especially with a elastic material. I know they have so many things that they label everything. Then there's this little spike, and then it goes down. And what it does is that's just right at the point where you've lost its strength. It spikes up a little, and that's the ultimate tensile strength. Now, with a more brittle material, it's hard to find that. These kind of overlap to a point. Then you get your percent elongation, determines the ductility of a material or how much it can stretch before it finally fractures. So then you do that, and then let's say it's still bending and stuff, but you've reached that ultimate tensile strength, because that's the part you want to know. What's the most strength, the most stress you can put on this thing, you know, where it spikes up there. Then it keeps going down. It keeps going down where it's losing its strength, but then finally it rips, and that's the percent elongation. How much can this thing stretch, you know, where it's been strained, okay, and then before it cracks. So you got it. So here's kind of where it flattens out, and it just has more strain to it. Even if you just keep the stress the same, it just then here's where it spikes up to its the most stress that you can put on it, and then it just goes down, loses its strength, and here's where it finally it stretches so much it starts to fracture and rip and all that. So anyhow, trying to put it in layman's terms, it's kind of difficult. Now there's different types of tensile testers. Ours, we had the square flat specimens, and then you'd cut them in an hourglass shape, and then they come back and it would hold it between the two. This one is a type round part that you thread into both of these, and then you stretch it. And then what they usually do is have little holes punched in here, and then you can measure how much and where it actually, depending how far these are apart, how far it stretched and where did it stretch. Did it stretch more in the middle, or did it stretch more towards the ends? And it's always more of an hourglass shape, because if this was totally straight, this piece, then it could bend and break right here where it's threaded inside the machine and break that mechanism and all that. So that's why they always have an hourglass shape to it. Okay, we get into wire drawing. Now, a metal reduction process in which a wire rod is pulled or drawn, that's what we call wire drawing, through a single die or a series of continuous dies, thereby reducing its diameter. The length of the wire increases as its diameter decreases. So you're not shaving the material off any. If you're making it thinner in diameter, well, the metal's got to go somewhere, so it just makes it longer. It's just like when you take a little piece of bubble gum, and you know how kids take it and they're playing with it and they stretch it out. They didn't lose any bubble gum. They just made it, you know, that little piece that they had is now stretched all the way across like this. And they slap it on the back of your nice upholstered seats, and then it sticks there. And they're not leather or anything. They're fabric, and then, you know, it's real hard to get it off. And then you want to beat the kid, or you just, you know, when you take them to the zoo, you just want to leave them there and pretend you never knew them. But, you know, it is your neighbor's kid, and I guess you do have to return them or you'll get in trouble. All right, well, anyhow. Fine wire drawing machine. So this is an example of one. Basically, it can go through. Now, what happens is if you're going from a real large diameter to a small diameter, you don't do it all at once. You're going to crack and break it, so you progressively do it. And that's what they're showing you here, is they get smaller and smaller dies. This is kind of schematic, okay? You got thicker wire, goes through the die, it's angled there, stretching it, and you got thinner wire, and of course, you're going to have more of that wire because the material had to go somewhere. You have a mass, and if it got smaller in diameter, then it's got to increase its length. So you're going to have a bigger spool here. And then it's showing you where it's pressing that down, and shouldn't be losing any material. And the other thing is, this wire is going to be what? If it's being pressed and cold work there, it's going to be more brittle. It's not going to be as soft. So you have pretty annealed soft wire when you start, and then that makes it a little harder. That's why sometimes if you're working with electrical wire, you bend it too much and it snaps off. But you want you don't want it too loose, because then you can't form it well. So there's a point to where, how hard do we want this metal? Alright, so anyhow, pulls a wire rod through a die, reducing its diameter, increases the length of the wire as its diameter decreases. May use several dies in succession for smaller diameter wire. Improves material properties due to the cold working, so it makes it a little harder. Wire temper can be controlled by staging, drawing, and annealing treatment. So yeah, if it gets too brittle, or you can't really bend it, then you may have to heat it up and cool it gradually. And so that anneals it and realigns the molecules, and it doesn't become as hard. Tube drawing's the same process pretty much. You can read this and fill it all in as you go along. The main difference is there has to be a floating mandrel in the middle. So you have your die, and then you have this floating mandrel, and so your material, your tube goes around that, and then that mandrel keeps hitting that die. It can't go through it because it's angled like that. Stays there. You go, oh, does it go with the piece? No, it's hitting that. And the reason for that mandrel, if it went through this, it would just cave in any which way, and it may crush it into a solid wire. So you want to keep it as a tube, so you have to put something in the middle of that to keep the nice round tube. And so you have also the thickness of the diameter of this tube is the same all the way around. If not, it could crush it more on one side, and you wouldn't have a nice even tube. Same thing, just better for tubes. And usually you're doing smaller sections, let's say copper pipe, in your house and stuff. You buy those, 6, 8, 10 foot lengths, I forget, really whatever you want them cut, but they're making smaller runs. Now, they also make the bigger spool copper pipe that when you're pouring your slab foundation and that, and they bend it every which way and all that comes in a big spool. Yeah, then they can go with longer lengths. And again, before and after, what makes it all. There's the floating mandrel in the middle. And this gives you an idea of all the dies and clearances and all that good stuff. So again, stock is pulled through a die, reducing its diameter, increases length as diameter decreases, may require several passes. Big thing is it has that floating mandrel, and then of course it'll get a little harder because you've been doing that. So anyhow, then we get into stretch straw forming. So here the cold forming of sheet stock over a forming block with what they found out is, you can stamp fenders and dies and whatever, big metal presses and that. If you hold that piece of metal and put tension on it where you're pulling these things apart each way, so you're putting tension on that whole piece. They did this by accident. Before they were just trying to grip it enough so when they were stamping, that piece didn't spin when they were stamping and all that, and so they kept adjusting it and tightening it. And they realized that when they did that, it didn't take as much force to stamp it, because that thing was under that tension of that, holding the pieces apart, pulling it apart. So that's it. It's holding it there and putting pressure, where it's pulling it apart, giving it tension. Boom, boom. And there's the before, and there's the after. Plus, when they stamp it, like here's where there's corners, and let's say you're doing something really deep, it wouldn't crinkle as much around those corners by doing that. The other thing too is you can use, you don't have to have real hardened dies for it, depending on what you're making. You could use wooden dies and stamp it. You wouldn't need as much pressure. So if you're just making a short run, one of it or something, you're good to go. Now there's hydraulic, where they can use hydraulic fluid and smash this. They can use this, let's say you're making a big 300-foot diameter dome top for the courthouse, or Capitol building or something, and you do it in a big tank, and you can use water, and then you could have just a wooden mold, and then you have an explosive charge you put in the middle, and because water pressure is even all the way out, like with fluids like hydraulic fluids, when that thing explodes, it puts enough pressure on that metal where it fills up that empty cavity, if you have it formed like a dome. Also, thinner stuff, you can use electromagnetic coil and do it. So it just depends. It's a way to save money. So it uses flexible, low-cost tooling, produces large parts at a reduced weight, reduces material thickness, obviously, because you're stretching it 5 to 7%. The yield strength's a little better, 10%, and requires less forming pressure. All right, then we get into terms and definitions of forming. If we're bending something along a straight thing, we have our brake. Okay, B-R-A-K-E. And here's one, I guess it's a hydraulic type. We press the foot control and it'll automatically bend it for us, which is kind of nice. Now some other terms, if you slightly bend a piece of sheet metal, you put a crease in it, gives it a little strength, just like clothes. If you put a little crease in it, it makes it a little stronger right there. If you have one of these cotton shirts like I do that the dean's office gives us, they're 100% cotton, and yes, you have to really iron them and put lots of starch in it. This looked good this morning, and now it's already looking wrinkled. But anyhow. A flange is, let's say, two pipes come together, or this little ductwork comes into another ductwork, and you see there's holes, and then you can put bolts in there, or you can weld it around. But usually you see big pipes where they have all these massive bolts in there. Put something together on a pipeline. So they have this flange. That's this part that from the pipe that comes out on the edge, 90 degrees, or it could be just a stiffening edge. Hem is when something's folded over 180 degrees. You just bend it over 180, not 90 where it's up, then you go another. Stiffens that edge, plus if the sheet metal's cut, it's got a sharp edge, so you want to put a rounded edge. Let's say on our tool tote trays that we made a hem there on that edge where our hands would come in and pick up tools out of that tool tote tray, so we wouldn't cut ourselves all the time. And so we just fold over the sheet metal, we're good to go. Plus it makes it look stronger too. So you've probably seen big duct work where they put these X creases in it. It gives it strength, because if not, you have this big flat piece, and as you turn on the air conditioning and the heat, that air pressure moves and boom, boom, boom. It'll go boom, boom every time you turn it on. Sometimes you'll see that in some homes or buildings. They didn't put a big enough crease in it. And so every time you turn on the air, and boom, you hear that noise. It's terrible. Again, there's our flange. Curling, you can put wire in there and curve it around. With this wiring part here, you just try to curve it the best you can. And then there's your hems. Seams, you fold it over like kind of a U shape there, and then the other one's a U shape, but it comes out a little bit so that can fit flush. And then you can fill that with some solder. See, like you see your tin cans have that sometimes where they're seamed together. Soup cans and stuff like that. And then here, if you're connecting one piece to another, and then you can solder that. Or it's just pressed in there, stamped down in there, and then it's good enough usually. Depends on what you're doing, what you're making. So, anyhow. Seams used for assembly, tabs, narrow area, produced by notching. I told you that we bend out, and then the other piece can come into it. And then this little tab comes on top of that, and then you can spot weld those pieces. Commonly used for assembly. Theory of bending, oh boy, yes. Forming is not an exact science, as you saw with that sheet metal when you guys cut it, and it's hard to get it all exact and perfect, and when you bend, it springs back a little bit, so you have to bend it further than 90 degrees to get it just right. So yeah, variations in the stock thickness causes it not to be exact. Variations in the surface finish, lubrication, material strength variations, because again, usually any metal is a mixture of recycled metals and that, so you don't know exactly the quality that you're getting. Brake forming, and we had a little brake there, and box and pan brake. You can take out these little fingers so you can bend it and not affect the other parts and get them together. If you've got one part that's bent out this part and you only want to bend up this side, if you don't take out some of those fingers, then that's going to hit that and bend the whole piece. And so that's why all these little pieces here come out. You know, with a Allen wrench, you can loosen these nuts and take out some of these fingers in there. And you probably have no idea what I'm talking about, but if you've taken the class or will take lean production, when you make the part, you'll see what I'm talking about. Now here's one, and to fold it, if you're thicker materials, it's hard to bend a big long piece, so they put these little weights on there, so when you fold it, it's easy to fold. Or you can just get a hydraulic one, you press the foot, use your hands to hold the sheet metal, and then you press the button, only it's a foot control, and you press down on that pedal, which presses the button underneath it, and then it'll bend it for you. Watch your fingers though. And you know, you can do all kinds of things. You can make them computer, CNC operated, the whole 9 yards. Here's before, and then you bend it, and you can bend it again. And there, now you got that nice little part of a box that they're making. So anyhow, you can't beat that. You know, it's a little better than my other ones there. I saw that moving one. I just had to have it. All right, so anyhow, depending how you have all those blades set up, you can make a nice edge like that, a curved edge, you name it. You can have tolerances up to 0.02 of an inch. You know, it's not bad. And it shows you required 4 tons. So if it's 1/8 inch, you know, versus the sheet metal we're making, yeah, you need 4 ton, 1/2 inch, 60 tons. So you're not going to be doing that manually. Production rate, how much you can run through there, bends per minute. Obviously, the thicker it gets, there's more positioning and moving, and it's harder, it's heavier, it's not going to go as fast. So it's going to take you a little longer. Aluminum's a little lighter, so as you can see, it's a little more. You can do more than you can with steel with the same thickness of material. Okay, so brake forming, to sum it all up, forms ductile material, which is bendable material, requires minimal tooling, can produce, you can see that U, V-shaped, or even special punches and dies. Is suitable for production of small parts, is used for low and medium production, may use special application dies, interchangeable press brake dies, and numerical controlled machines, CNC machines. All right. Then we get into progressive roll forming. So we start out with a flat sheet, and as it goes through, it bends a little more, bends it, curves it around, and can make a gutter, you name it. You'll see all the things it can make. So progressively, you don't try to bend it all at once, or it's going to rip the metal. And so you have these stages of dies, or rolls, as they call them. And then we have some videos. Let's see if these are going to work. Okay. So what we got here. Here's one. They flipped open the guard so you can see it. And to help form, you'll notice that they have some type of coolant that comes down to keep everything cool, the same, so it doesn't get too hot. And they start out with this one strip of metal, and it runs through, and it forms like a U shape, and it curves around, and automatically cuts it. I guess for the top of a barrel or something. Pretty slick how they kind of angle this too, so it comes around and cuts it exact. Boom. pretty neat. Yeah, this plexiglass cover goes over it so you can see if there's any issues. What they're trying to do is make all the guards plexiglass now, so when you cover it, if there's a problem, you can see it happening before there's an issue. This thing can bend this stuff all day long. Look at that. And come down and cut it. And you can't beat that, huh? Kind of like setting all that up. That'd take a while, wouldn't it? Yeah, well, that's why you have the company rep set up what you're going to do first. And you make sure you understand what's going on. Have 3 or 4 people see what's going on. And then you're good to go. And you can do this all day long. Looks like he's excited about it. But look, it makes it perfect. You can't even tell what he's showing you where it's been cut. I mean, it's so perfect. Look at that. It's U-shape. Must cover some barrel or something. Pretty slick. Pretty neat. Okay, let's see later what they do. Oh, they show you that. They make it so perfect, this process. Look how it follows the other one. I mean, it's exact. You know, instead of it all being a little cockeyed, a little crooked and stuff. I mean, it's perfect. Look at that. All right, enough about that one. All right. All right, so we'll continue on. Oh, then here's another one. So let's click on that before we lose our Microsoft. Please. No, it's not going to let me do it. Yeah, okay, try it again. Oh, that's not good. All right, that's our punch press. I remember that, didn't I? We'll get back to all that good stuff. Sorry about that. Can only handle so much. Luckily, this computer is better than the other one I had. I'll tell you that much. It used to break down every time I turned around. And here's another one. Let me just see what this does real quick. It's worth it. I didn't like that, did it? Oh, maybe it will. Okay, maybe we'll play. We'll see. I'll see what this makes. Oh, I know I want to show you this. If you have a process that's continually moving, when they're stamping pieces out on this flat piece, watch how, when they're punching, they have to move with it to cut it. See how that flex, and then it's got a spring that pulls it back. So, because if you're cutting something, if you just stop it right there, and it's still pressing, it's going to kink up and make a mess. So when you're punching, you have to move with it and then come back. Move with it. So that's what I wanted to show you. And look at all of this. It's taking that metal, curving it up. I think these are the things you put in where you have the adjustable shelves and have little holes for the screws you put in, and then you put in your little holders for that. So that comes up. You have to punch the holes for the screws. And then it cuts it to the right length. You know, it could be drawer slides too. I mean, I don't know. But anyhow, what I'm trying to say is, whenever it's doing something, it has to stay with that pace. So I thought that was kind of neat. Maybe you didn't, but that's okay. As long as you say it's great, Dr. Miller, we enjoy it, then, of course, you get a curve. All right, so again, your coiled strip, and then all that you can do with it, you can even curve it all the way around. Progressively move that around. Okay, I think we get the drift. You try to do it all at once, like I said, it'll rip and tear it. You gradually do it, it's fine. It's like when you're making something. You try to make it all one day, you're worn out. You have to gradually do it. So used for mass production of long pieces with close tolerances. Utilizes, again, flexible ductile workpieces. Usually less than 1/8 of an inch thick and 20 inches wide. So it's usually less than that. Produces workpieces at a typical forming speed of 100 feet per minute or more, or less, but It's amazing. It's suitable for decorative and structural products. Then we get into plate roll bending. This one is interesting for big thick plates, or for sheet metal too. We had one where you can bend a nice round piece quickly just with this one piece. And they have 3 rollers that you have, and the one in the middle you can adjust how close it is depending on the thickness of your material and at what angle you want. So you could either make a straight round piece, or you could have it set at an angle so where it makes a cone shaped piece. So here's a bigger one for doing thick material. Say it's in a pyramid formation is what they're showing you. 2 rolls down here and the one in the middle, or on top in the middle. Depending on the access, there's some that have 4 rolls. I guess is what they're showing you here. I guess you can get closer tolerances with it. And then this can flip up and you can slide your rolled piece out. Okay. So if you look at a 4 roll, I was showing I guess this is the Heller brand where they have 4 rolls versus the typical 3 rolls. And they're kind of newer on the market. But you can get tighter, closer tolerances with it around your rolls that you have. And it's showing you big, thick stuff. See that big piece there? This big piece. We were watching when I was in Corpus. They were making these big, and they probably have it in Longview too, where they'd make the big tanks for rail cars. And they bend this all in one piece, and then they weld the 2 ends on and the top part and fill them. And some of these were, in fact, thick plates. Some were thick stainless steel, depending if they carried milk and stuff that you wanted to be able to clean out, and orange juice and, you know, nice items. So it just depends on what you're making. Pretty cool. It made these big things. Yeah, you could hear it when it was working. So again, here it's making like this one's adjusted more than the other, and so it gives you a cone shape. This one actually has ridges in it, so it may want to strengthen the material. It's a thinner material. They want to give it more strength. So you can do grooves and cones and all that. So anyhow, before, after. Good for plate, good for sheet metal as well. And again, if it's bending this way, they can only bend this way. You try to put it the reverse way, it's not going to work. So if you look at this, up to 6-inch thick material and 20 feet wide or bigger, depending how big you want to make this, but typically that's what they're saying. Material greater than a 1/16 of an inch thick end. So it typically uses material greater than a 1/16 of an inch thick and 15 inches wide for this. Or you could use other processes that are more affordable, economical for what you're doing. Utilizes any material capable of cold working that you're able to bend it, and primarily used in forming large cylindrical sections requiring the seam to be welded. Yeah, obviously you got to weld that seam together. Then we get into drop forging. It's kind of neat, where you have to heat up the material and then hammer it, and then keep hammering it until you get it to the right shape, which I'll show you. Hopefully those videos work, because that's kind of interesting. A job that everybody wants. A metal shaping process in which the heated workpiece is formed by the rapid closing of a punch and die, forcing the workpiece to conform to the die cavity, which you'll see in a minute. The workpiece may be impacted in a sequence of punch and dies, and you'll see that. It takes a while to get it, to form it. It takes a lot of pressure, and depending on what you're doing. So let's say here's the punch, you put it in, bam, 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 till you get about the right shape. There's usually a little bit of flash. You'll have to grind off, cut off, whatever. And it shows you here a connecting rod, let's say for an engine. You start out with the tongs. You're holding this molten cherry red hot piece. Bam, hits it once, bam, hits it again. And sometimes it's got, like, you hit it in this one part of the die, then the next part, 3 and 4. Boom, boom, boom. See how progressively it gets deeper. And then the last time it may be the die where it cuts it and cuts the flash off too. And then you may have to do some minimal grinding on it. Yeah, here it's showing you. Boom here. Wait, here first, boom. Second, boom, you get it kind of close to the shape. third closer, and then fourth gives you more definition. Again, holding these with some metal tongs away from this, because you'll see how hot it gets. Usually there's a furnace right next to it, and they pull it out of the furnace when they get it the right color, the right temperature, and then bam, 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 they hit it. And here's a big forging press, which you'll see in a minute. Oh, and here's like a person. Sometimes they're about this big. Yeah, this big. They get their tongs in there. So anyhow, let's see if this works today or if it's going to shut everything off. Well, maybe it will work. All right. Yeah, there you go. Boom. Get their little long tongs there. Adjust it. Then the oven's right over here. We took it out of the oven and bam, bam, bam. This job will keep you in shape. Hopefully they have their hearing protection in there. Don't want to put your hand in there either. There, it's taken out of the oven now. Then this guy takes it from there. Oh. Usually there's a little graphite lubricant on there so the cherry hot doesn't stick to the metal die. And so the initial one's got to kind of like spraying it in there. Or sometimes they do it with a liquid or an oil. Usually graphite works good for that. The thing, it's on a cam, so it keeps moving all the time. And then when you press the pedal, it comes all the way down. Boom. Initially, when it first cools off, the first time it hits that graphite, it makes that big cloud of smoke and all that. Sometimes the graphite's mixed with water, sometimes it's mixed with oil, or sometimes it's just a dry powder you put in there. So, as you can see, another Hollywood production here, but you know, boom, look at that. Just makes you want to go and get a job there. That's why you're going to college. I was in a place that did this. We did casting and forging at the Chevy Tonawanda plant. Making those Concord Vega. Well, I did an internship there. I was ready to get out of that one. Paid good, but I don't know. Watch this. Boom. I think we get the drift. Alright, let's head back. It's enough noise for the day. Alright, oh, and then this one. What was this one? Is this one better? Let's see if there's anything better. Oh, this is smaller. Let's see. Trying to see if they're doing better. And they spray some graphite lube on it. And this guy maybe just spraying air, cleaning off some of the junk on it. Or a combination of the both. See how hot it is? I mean, look at this thing's on fire. Yeah, there he is. He puts the graphite powder on this one. He's just slopping it on there with his hand. He's got that down to an exact science, doesn't he? Man. Now it's sticking. Alright, so anyhow. You can watch these all day long, but interesting. Very interesting. Okay, I think we've seen all of our good stuff for that. Alright, keep it moving. the effects of drop forging, because you're heating it up and hammering it, you're smashing it, and you're keeping the grain because you're gradually cooling it to makes for what creates good to excellent mechanical properties, including fatigue and impact resistance, may create micro cracks depending how well you do it. But that's why you saw those connecting rods for your pistons and your engine that goes to the crankshaft. You can get, and same with the crankshaft itself, you can get them either cast or forged. Well, what do you think you'd want? Cast, that's just pouring molten metal in. You could get bubbles in it and what have you, and so it may not be as strong. When it's forged, and you'll see this for all the racing vehicles and stuff like that, anything that's going to have some high RPMs, it's usually forged because it's heated up and smashed down and heated up and smashed down gradually, and so it doesn't affect the grain structure. So it's super condensed and strong, so obviously it's going to be a lot stronger than something that's just cast and could have bubbles in it and air bubbles in it and not be as strong. It could easily break. So again, it shows you the manual tongs. Sometimes it's real heavy. You're going to have overhead cranes help you with mechanical slings to move the stuff around. I think there was another film, but I think you got the drift of what forging is all about. Anyhow, different lubricants. For aluminum, you can use kerosene oils with the graphite in there. Mild steel, again, you have the graphite suspension, but sawdust, oil, salts combined with that, and you can spray it on. Or you saw that guy just taking his hand and dumping it on there. Stainless steel is pretty good. You don't really have to worry about it. Magnesium, again, a graphite suspension, but usually mixed with a vegetable oil. And that's good because it makes it easier to recycle the less toxic stuff we have. And they spray it on each time. And then this is just for titanium, some extreme pressure type oil. So again, gradually forms heated metal by singular or repeated blows, as we saw, in a sequence of individual or multi-stage die cavities. Produces a parting line, which is that little edge that's squeezed out, and so you're going to have to remove that flash. Typically requires machining to obtain dimensional tolerances and good surface finish. Extrusion is just like with plastics or your toothpaste, where you have this big tube and then there's the little orifice at the end, the die cavity, and when you squeeze it out, it takes the shape of that, like toothpaste. It's a round hole, so you're going to have your toothpaste come out in a nice little round section. Low yield strengths at extrusion temperatures would be lead, copper, aluminum, magnesium. Steels and stainless steels are more difficult to extrude due to their high yield strength. So obviously these are softer materials, especially lead. And then they're showing you here, sometimes you may have to use heat, obviously with metals. Lead not so much, but for the other stuff, because you can't press it. You can't use a steel die to press steel. So you're going to have to heat it up a little bit so it makes it more flexible. And what's cool is, depending on how you have your die set up, you can have real intricate stuff. Let's say this stuff comes out in 20-foot lengths, 10-foot lengths, or whatever, then you just cut it to length. And you've got all these different parts, extruded assemblies for window frames. You've seen aluminum window frames, or connectors for desks and stuff, you name it. Here there's direct extrusion, where when the rams squeeze it, it comes out the die opening, and that's what you get here with the indirect, where the ram squeezes it, then it comes out the backside of the ram. So, wide variety of shapes can be produced. No draft is required, no draft angle. Extrusion dies are relatively cheap. Good dimensional tolerances, 0.003 of an inch, plus or minus. Strong directional properties as you're squeezing it through, so it's pretty strong, the material, when you're through. Cross-section must be the same for the entire length of the product, so nice way of making it. And that's all we have. There'll be a quiz on that as well. So, and I think there's 3 quizzes because then I take all the different processes together. So, and that should wrap it up for these type of forming process. I don't think it wraps it up. But anyhow, we'll keep it moving.